In this video, I'm going to set up a two-way FSI analysis of a deformable leaflet inside a fluid channel. This simulation is based on a numerical investigation done by Mr. Wang et al., which is originally a 2D simulation, but in order to do this simulation in ANSYS Workbench, I will have to consider a unique third dimension for this model, and I'm going to use 2.5D dynamic remeshing technique in ANSYS Fluent for this simulation. The geometry of computational domain is shown in figure 6. Fluid channel has 8 centimeters length in x direction and 2 centimeter width in y direction. The solid part is fixed from the bottom, and the height is 1 centimeters and width is 0.5 centimeters. The solid part is 3 centimeters away from the inlet, and airflow comes through the inlet with uniform specified velocity and hits the solid part and causes it to oscillate and then exits from the outlet. The time history of deformation of the top left corner of the solid part will be measured as a result of this simulation, and all of the material properties of both solid and fluid domains is given in this article. Let's start the simulation with sketching the geometry with Design Modeler. I'm going to use transient structural for solving the solid part and fluid flow fluent for my fluid part. Let's start with giving some material properties for the solid domain. I'm going to rename this structural steel to, for example, material. And the density of the material based on the article is 0.1013 grams per cubic centimeters. So let's just change the unit to grams per cubic centimeters, and the value would be 0.1013. Young's modulus is 100 Pascal and Poisson ratio is 0.3. Let's start drawing the geometry with Design Modeler. I'm going to use XY plane for creating the sketch. For fluid part, I have a rectangular shaped domain with the dimensions of 8 centimeters in x direction, so h1 would be 0.08, and in y direction I have v2 with the value of 0.02 meters. So this rectangle represents my fluid domain. I also have a little rectangular shape here. The distance between this line and inlet is 3 centimeters, so h3 would be 0.003, and also distance between this line from the inlet would be h4 0.035. and the height of the solid part is 1 centimeter, so V5 would be 0.01. In the fluid domain, I have this little extra edge here, and I can just remove it with trim tool. So sketch 1 is my fluid part, and I'm gonna use another sketch for my solid part. Sketch 2 is my solid part. Let's use rectangle for drawing the solid. So I'm having two sketches here, one for fluid and second for solid. I'm going to use extrude tool to create a three-dimensional body for sketch 1. The depth along the Z direction, this is the dimension which I was talking about, the third dimension. It would be 1 centimeters. Actually, this is for my solid part. Sketch 2 is extruded, and I'm gonna use another extrude for creating fluid part. In order to prevent merging these both parts, both bodies, solid and fluid, I will be using add frozen. This prevents merging two parts. So I have here two parts. This is my solid and this is my fluid part. I can just rename it to fluid. In order to define my dynamic and static zones in fluid domain, I'm going to slice the fluid domain with the using of some plane. In YZ direction, I'm going to create a plane. Offset Z with the value of 0.029. I'm gonna create this plane. Also another plane. This would be offset Z with the value of 0.036 maybe. And also another plane here. The third one would be ZX plane. Offset Z with the value of 0.011. Create, and I'm gonna slice the fluid part with using of these planes. So I click slice, all bodies generate. And for this slice, I just want to slice this part, so I use a slice and use selected bodies. I select just this body for slicing and click generate. Here I have a fluid domain with 1, 2, 3, 4 parts and a solid domain with just one part. So these parts would be my fluid domain. Let's click all of them and form a new part here, and I'm gonna rename that as fluid part. So the geometry of both solid and fluid domains is created, and let's start with transient structural. First of all, I will suppress the fluid part because I have nothing to do with the fluid part in transient structural, so I'm going to suppress it and make sure the solid part, the materials which is assigned to solid part, is material that I just gave the properties in engineering data. I'm going to start meshing with some edge sizings. Ten divisions with hard behavior in this direction, and $20 divisions. And Z direction, gonna use 5 divisions. I also can insert meshing method. I'm going to use sweep method. Face mesh type all quad, and number of divisions 5. Let's generate the mesh. This mesh is pretty enough for the simulation, so let's check the analysis settings. Step end time would be 1.4 seconds, and auto time stepping would be off, and time step size would be 0.01. The bottom of the solid part would be fixed, so fixed support will assign to the bottom, and I'm gonna insert fluid solid interface. These faces would touch my fluid domain, so these are my fluid solid interface domains. And also I'm gonna insert some directional deformation results for left corner of the solid part. And I can see the deformation during the solution with deformation plot tracker. So all the settings in transient structural is done, and next part would be meshing the fluid part. Let's connect the geometry to fluent and start meshing module. First of all, I need to suppress my solid part and start meshing with giving some edge sizing. These edges, I want to divide them with 10 divisions. With hard behavior, or maybe these two edges also I want to divide them with 10 divisions. So I have 10 edges with 10 divisions with hard behavior. Also these edges I want to divide them with 20 divisions. with hard behavior. And also these edges from inlet and outlet with 30 divisions, hard behavior. If I want to have finer mesh at the bottom of the fluid domain, I can use bias for these edges with bias factor of 3. Some of these edges need to be reversed. The bias need to be reversed, so the bottom has smaller divisions and the top has bigger divisions. Also, these edges, I'm gonna divide them with 20 divisions, and if I want finer meshes near the solid part, I can use bias for these edges too. So with hard behavior, I'm gonna use this bias with bias factor of 3, and I must reverse the bias of some edges. These two edges must be reversed. Also these two edges. So I'm having these divisions, and I will have finer mesh near the solid part. In order to use 2.5D remeshing technique in ANSYS Fluent, I need to choose a meshing method which creates elements in source faces and extrudes them to the target faces, so we can have exactly the same elements in the thickness of the fluid domain. For this purpose, I'm going to choose sweep method. In this simulation, the fluid domain has two parts with static and dynamic behavior. These parts, I'm going to name them as my static parts, and these parts, which will be meshed with triangular elements, would be my dynamic part. So I'm going to use quad meshes in static parts and triangular meshes for my dynamic part. So I'm selecting these three parts as my static parts and use sweep method. Sweep method, and I'm going to define source and target faces. These are source faces and these target faces. I want to mesh them with all quad elements, and my mesh will be divided along Z direction with 5 divisions. So my static part will be with quad elements, because ANSYS dynamic mesh cannot remesh quad elements. So in my dynamic part, I'm going to use triangular elements, but it's okay to use quad elements in static part. Another sweep method for my dynamic part, this part would be my dynamic part. So sweep method, manual source and target faces. These would be my source face, and this would be my target face. Elements will be all triangular, with the division of 5. So let's generate the mesh. This quality of mesh is pretty enough for this simulation. As I said, these parts, these 3 bodies, are the parts with static behavior. The mesh will not change, and Fluent will not remesh these 3 parts. But this part is my dynamic part, which dynamic mesh will be applied for this part. Let's create some name selections. This face is my inlet. I'm gonna name these faces as symmetry 1, these faces as walls, these 3 faces as my fluid and solid interface. I'm gonna name them as couple. This face as outlet, and these faces as symmetry 2. Also, I'm going to name 3 bodies as static part, and this body as dynamic part. So with this meshing, I have inlet, symmetry 1, walls, couple faces, outlet, symmetry 2, static part, and dynamic part. Meshing of the fluid domain is done. Let's close the meshing module and start Fluent setup. I enable double precision and put 2 solver processors for the Fluent. This simulation is a transient simulation, and the viscous model is laminar for this simulation. In material properties, the property of air must be changed. The density is 1.3 and viscosity 1.8 E-5. In boundary conditions, I have velocity inlet. The inlet velocity magnitude is 0.2. Outlet boundary is pressure outlet, and the gauge pressure is 0. In dynamic mesh settings, I enable dynamic mesh and use 2 methods, smoothing and remeshing. In order to use 2.5D remeshing method, the smoothing must be on spring method. Spring constant factor is 0.5 for this simulation. I enable 2.5D remeshing and copy mesh scale info into the parameters. The setting of the dynamic mesh is done. Let's create some dynamic mesh zones. Couple faces are deforming faces. Their deformation is defined by system coupling. In solver options, solution stabilization is enabled. Scale factor is 1 for this simulation. Dynamic part is a deforming part. I disable remeshing for dynamic part. Dynamic symmetry 1 is also a deforming part, and remeshing must be enabled. I choose plane definition method to define the geometry of dynamic symmetry 1 to dynamic mesh settings. If I want to define a face with a plane, I need a plane normal and a point on that face. The plane normal for dynamic symmetry 1 is 0, 0, 1. And in order to see coordinates of a point in dynamic symmetry 1, I make some changes on display menu. I disable the display of all other faces and enable just dynamic symmetry 1 with its edges and nodes. If I right-click on a mesh node on dynamic symmetry 1, its coordinates is shown in console. I just copy x, y, and z values to point on plane. Remeshing for dynamic symmetry 2 must be disabled, and its geometry definition is same as dynamic symmetry 1, except the point on the face. The z value must be 0. Static part has a stationary mesh. Also, static symmetry 1 is stationary, and static symmetry 2 is stationary as well. Dynamic mesh settings is completed. I changed transient formulation method to second order implicit and initialized the solution with hybrid initialization. After initialization, I can have some calculation activities. I want to save data quantities in every time step. I want to have static pressure, pressure coefficient, total pressure, and velocity magnitudes. I also can see velocity changes during the solution. It's creating a new counter object, velocity counters. I want to see velocity counters on dynamic symmetry 1 and static symmetry 1 during the solution. I can simply adjust the display. Now I can see velocity changes in every time step during the solution. I also can add another animation. I want to see mesh changes during the solution on dynamic symmetry 1 and static symmetry 1. In Run Calculation menu, I can define the time step size and maximum iteration. Number of time steps is overridden by system coupling. The Fluent setup is completed. I can use system coupling to couple Fluent and transient structural. In analysis setting, end time is 1.4 and time step size is 0.01. I put 10 iterations for system coupling. Couple faces in Fluent and fluid-solid interfaces in transient structural are the phases that data transfer will occur during the solution. I create data transfer for these two phases and update the solution. After system coupling run completed successfully, now I can see some results in transient structural. Time history deformation of left corner of the solid part is shown in the graph, and its values is shown in a table. I can just simply copy these cells or export them as an Excel file.